Right. Hi, everyone. So we're very happy to have the third talk of this morning by Carlo Collari from University of Pisa on weight systems, which are quantum states. Carlo?
Thank you, Isham. Thank you, the organizer, for this conference and for the opportunity to speak. I will be talking about weight systems, which are quantum states. It will be a simple story, yet a nice story. Where everything we expect to happen happens, which is always nice. Before introducing the problem and motivating it, I have to introduce some objects. Weight systems are usually dual object to what's called chord diagrams. In our case, we'll be dealing with horizontal chord diagrams. These are vertical lines, not horizontal, which are called Wilson lines, and possibly some horizontal line joining pairs of these Wilson lines, and these are the chords. Okay? So we can compose chord diagrams, horizontal chord diagrams, in the same way we compose braids. We just stack them on top of each other if you have the same number of strands. This endows the space, the complex vector space generated by chord diagrams with the structures of a non-commutative unital associative complex algebra. All fine and good. To obtain the algebra we really want, that is the algebra of horizontal chord diagram, we have to quotient binomial, which is generated by two types of elements. Those of type 2t and 4t. And these are called infinitesimal braid relations. These elements are, roughly speaking, of this form. 2T stands for two-term relation. Those which are familiar with the theory of quantum weight and Vasiliev invariant probably recognize kind of the relations. And 2T terms are commuting relation. I also have to point out that this is not the only thing appearing. We have also chords commuting if they are contained in each other. That is, this is also a relation. Okay. And the four-term relation is a slightly more complicated relation, reminiscent of the braid relations. Okay? Perfect. We have our algebra of chord diagrams. And this algebra can be endowed with a star that is an involution, which we extend it to be antilinear. And this involution is given by reading a diagram from, instead of bottom to top, from top to bottom. And this is an involution and endows our algebra with the structure of star algebras, which is an algebra where a ring with involution endowed with an involution itself, such that this involution preserves the identity, is antilinear, and is an anti-homomorphism of algebras. Okay, so far so good. A morphism of star algebra is what you can think of, just a morphism of algebra which commutes with this star involution. And we have our star algebras, but we want other examples. For instance, you can take the group algebra of any group ring and take as star the one which inverts all the elements in the group and conjugates the coefficients. And it will give you the structure of star algebra. Okay. Of course, if you are familiar with Hopf algebras, you will notice that this involution is nothing more than the conjugate of the antipode of the Hopf algebra, G, where the co-multiplication is actually the group-like co-multiplication, and the co-unit sends all elements in the group to 1. Okay. It's actually a very general fact that any Hopf algebra if we take the conjugate of the antipode and those the Hopf algebras with the structure of star algebras. And actually, and this is the interesting part, our algebra of chord diagrams actually arises exactly this way. In fact, Kono proved that the algebra of chord diagrams is actually isomorphic to the homology of the loop space of configuration space of points in R3. And this identification endows AN with the structure of Hopf algebras. Here, the multiplication is given by composition of loops, and the co-multiplication is just induced by the diagonal map, okay? And you can check that the star under this identification corresponds to the conjugate of the antipode, okay? So far, so good. So this identification actually gives us the motivation for this talk. In fact, Urs and Isham noticed that under the hypothesis H, we can identify AN as a set of observable, AN, yeah, as the set of observable of certain brane intersection space. In fact, the phase space in this case is homotopy equivalent to this disjoint union of configuration space. So if we interpret observable as the homology of the phase space, we get that the algebra of chord diagrams is in fact the observable in this theory. Okay, so this gives the interpretation of horizontal chord diagrams as observable, which kind of motivates the following question. Well, when you have observable, we can consider quantum state, that is linear maps which are positive semi-definite in this sense, and such that their value on the unit of the algebra is positive. I'm not requiring a normalization condition here. If you want, you can just divide by this value and you will get a normalized state. So a weight system is just, by definition, an element of the dual of the space of horizontal chord diagram. So one can ask, which weight systems are quantum states? Among weight systems, there are those arising from Lie algebras, which are actually used in the theory of finite type invariant to recover quantum invariants. And so one may wonder, are weight systems arising from Lie algebras quantum states? So let me recall, remind you what the construction of Lie algebra weight systems. We need 3 ingredients: a finite dimensional complex Lie algebra, a AD invariant non-degenerate bilinear form, and an ordered collection of finite dimensional G representation, let's say ρ1, ρn, where this n is exactly the number of Wilson lines. This will be the labeling of the Wilson line with a representation. And given this data, we will associate a weight system. The basic idea is to construct an element of the endomorphism space of the tensor product of the VNs and take the trace to obtain a complex number. This is the usual story. Okay, how do we construct it? We fix an orthonormal basis. This is just an accessory data, not really useful. And associate to each chord an endomorphism. Yes. And this is defined as follows. We basically, if we have the chord joining the it and the j strand, we associate this endomorphism of the Vn, where in the it position and the j position, we apply the representation on the orthonormal basis, and we take the sum over all elements of the basis. Okay, This is a definition. It turns out that this can be extended to a well-defined morphism of algebras between AN, this should be the tensor products of the VIs. And the corresponding Lie algebra weight system is obtained by taking the trace. Okay. So this is the guys we are interested in. So first, we want to deal with the, first an example. If we take as algebra GL2 as pairing this one, the trace of the product, and we take the defining representation over C2, one can compute, let's give things names. So this is a basis if we add the identity. This is the matrix of the pairing. It's non-degenerate, everything is fine. We can compute an orthonormal basis, which is this one. And now we can explicitly compute what happens in this morphism between A2 and the endomorphism of C squared tensor C squared with respect to the basis, which is just the tensor product of these elements. Okay? If one computes it over a single chord, it can explicitly get this matrix, which is nothing but the matrix associated to the permutation of the two tensor factor, C2 and C2. Well, actually, this is what happens in general. So one can show that using this construction, if we take all the representation to be the defining representation of GLN, this construction assigns to each chord the transposition of the two tensors factor corresponding to that. So we have this thing. If we take the trace, what we get is actually that the wave system associated to the defining representation computed on any chord diagram is just n to the power the number of cycles in sigma c, where sigma c is the permutation you obtain replacing each chord with a transposition. Okay? There is one thing to be pointed out. By the number of cycles, I'm also considering the trivial cycle that is the fixed points. Okay? So you have to take into account also those. Okay, now I'm going way too fast than I expected. So yeah, why this is interesting? Well, you should expect this to be actually a weight system, okay? And it is a result. The first result I want to present is due to David Corfield, Isham, and Urs, and is actually based on analyzing this function as a linear function from the group algebra over the symmetric group and relating it to certain distance kernels in relative to the Kelly graph of the symmetric group generated by transposition. Let me be more precise. Okay, this is the result of Corfield, Isham, and Urs. The GLNC weight systems are actually quantum states. As we notice, we have this algebra of chord diagrams. We have this map, which associated to each chord diagram a permutation, and we can extend it to be a morphism of algebras. Okay? This is our weight system, and here we have a function which is just n to the number of cycles of said permutation. Okay, and what we pointed out above is that this diagram actually commutes. So this one is actually more than just a morphism of algebras. It's a morphism of star algebras with the structures I defined before. Even more, it's actually a morphism of Hopf algebras. In fact, here, the structure of Hopf algebra is given by considering the diagonal map. And here is the group-like structure. So these things actually commutes with the with a coproduct, okay? It can be easily checked that it commutes also with the unit, so, and the co-unit, so this is actually a morphism of algebras, and in particular, it induced a morphism of star algebras. Okay, now, this is also surjective, morphism of star algebras. So, since it's surjective, if this is a state, also this one is a state, and vice versa. If this one is a state, also this one is. So, our weight system is a state in the sense I specified before, if and only if this thing is a state. Okay, now there is a bit of rewriting this guy. So we want to study this function, this linear function, actually is eigenvalues, in order to prove that they are all either positive or zero. This way we will prove that this is a state. Up to a rescaling by a positive constant, we can actually write down this thing as follows, where this dc is the distance in the Cayley graph of Sn with the generator of the transposition. Let me recall you what this is. This is a graph whose vertices, one sec. So Cayley of a group with a set of generator is, yeah. I don't know if, is this better? Yeah. Cayley of a group with a fixed set of generator. This is a graph whose vertices are the set of generator, the elements of the group, and there is an edge between two elements if exists an element tau in our set of generators such that, I don't know, g tau equal to h. That is, they differ only by multiplication by an element of the chosen set of generator. Note that changing the set of generator will change the Cayley graph. And the distance we are considering is the shortest path distance in the graph. Now, these functions are being studied a lot, especially in the case where instead of all transposition, one considers only adjacent transposition. Those are the mellow kernels, I think. But the important point is that this function, the distance, is kind of invariant under conjugation. Okay, so it's a class function over the group of the symmetric group, and class functions are, and the kernel of class functions are well understood. In fact, we know the eigenvalues and eigenvectors actually of these guys. These are parameterized by partition of n. Each eigenvalue, the eigenvalue of a partition lambda has multiplicity, the characteristic function of the representation associated to lambda, evaluated into the identity squared, that is the dimension of the representation squared. And the eigenvalue corresponding to lambda can be computed explicitly, this one. That is some factorials, some exponential. This is a dimension, so it's positive. And this is the number of semi-standard Yau tableau or shape lambda whose, where the labels are lower or equal than n, where this big N is the n of GLN, the group we are considering, okay? Where little n is the number of strands or Wilson line, okay? And this actually, part of it is classical. I think this formula was just in Isham-Morse and Corfield paper, but it's a computation with classical Hooke formulas and some tricks. Okay, so these eigenvalues are positive or 0, actually positive. So this thing is positive definite and hence defines a state. Now, there is one thing which I didn't point out. Actually, Corfield, Isham, and Dorse studies the positive definiteness of this function in the more general case where this logarithm is replaced by a beta, which is also quite interesting because it goes through semi-definite phases, indefinite phases, and then eventually becomes definite. Okay, now we want to proceed to some more general weight systems. By definition, the tensor product to the representation works of a Lie algebra work like this, which tell us that the weights computed in a diagram where we have as a labeling a tensor of two representation can be computed also this way, okay? This is actually important for what we are going to say. So we define the tensor splitting, which is a morphism, delta I from a certain an to a I, where this is capital N in the notation above. So we take a chord diagram with n Wilson lines, and we obtain a sum of chord diagrams with the sum of these guys Wilson lines. Okay, how do you do that? Basically, we replace the jth strand with ij parallel strand, and we lift each chord into the sum of chords. Let me make an example which will make things a bit clearer. So let's say we apply delta 2, 3 to this simple chord diagram. So we have to replace the first Wilson line by 2 parallel Wilson lines, and the second Wilson lines by 3 parallel copies of the same Wilson line. And then we lift the chord to all possible way to join the 2 Wilson lines here with the 3 Wilson lines here. Okay, and this encodes basically the tensor product of representation. In particular, when we compute the weight system associated to the tensor product of the defining representation, it will be the same as computing the weight system of this operator applied to the chord diagram. Okay. Now, each representation, is it a well-known fact that each representation of GLN is actually given by 2 things. One is a representation of SLN, and hence a Young tableau, Young diagram actually. And a complex number, so representation of GLN are codified by a complex number, which we will assume to be 1, and a representation of SLN. This is a Young diagram. Okay, so to obtain the representation corresponding to a Young diagram of 1, what we do is to restrict the representation, the standard representation over C and tensor itself, the number of boxes in our diagram. We restrict this representation to to the image of an element which is the Young symmetrizer relative to the representation we are trying to study. Okay, and here will be the same thing. Basically, we will break down. Basically, to study the representation of the weight system relative to the representation of GLN, what we do is we study the weight system applied to the tensor product of to the tensor product of the defining representation. Then we apply something which codifies kind of the Young symmetrizer. Okay. Now, okay. So we basically, this is what I said. Oh, sorry. This is what I said. We basically encode the weight system in this way. Here we apply our tensor splitting, which brings us to the tensor product of this representation. Then we apply the Young symmetrizer, and then we apply, the morphism to the group ring of the permutations. Then we apply something which encodes the action of the Young symmetrizers, and then we apply our well-known state. So one hopes to obtain the same thing as in Urs, Isham, and Corfield result, and say something like, well, this is a morphism of star algebras. This is a morphism of star algebras. So this is a state. So if also this is a morphism of star algebras, we are done. Unfortunately, this is not a morphism of star algebra in any case, except for the defining representation. So we have to say a bit more of how the action of this guy works in order to prove that this composition is actually a state. And then we will be done. Okay? Now, let me describe briefly how that C rho works in an example. Okay, we take our favorite core diagram, and we want to compute the weight system associated to this labeling. Okay, so yeah. Yeah, this is definitely better. So we want to compute what I call WGLN, let's say lambda 1, lambda 2, okay, of this guy. Okay, so I apply first the tensor splitting. So I will obtain here a number of strands like the number of boxes in lambda 1. Here I will obtain a number of strands like the box in lambda 2. And I will have that for each I and each j, the ith cable here is joined by the jth cable here. Okay, so this is the guy after the tensor splitting. So this is the first step there. To this guy, we associate the corresponding permutation. So basically, we replace each chord by the switch. This I, this j. And here we have all the remaining chords, Wilson lines, sorry. And then we cap it off here with a Young symmetrizer corresponding to lambda 1, and cap it off here with with a symmetrizer corresponding to lambda 2. And then we take the trace. This is exactly how it goes. This is completely classical. What is the point? Is that in general, this symmetrizer complicates too much the situation. So one has to notice, this is what I just said, that this map is not a morphism of star algebras, but these symmetrizers are disjoint, so their action commutes, okay? And the symmetrizer square is by definition itself, by definition of symmetrizer. So if we suppose that our row are either alternating or symmetric representation, so in a very special case, not for every representation this work, then we have that these things is dual, is a self-dual with respect to the star, okay? Now, if you have that like self-duality here and these properties, then you note that this guy is actually a morphism of star algebras. Because every time I apply Wn of C to A star, then this will be Wn of C square A star, and this, since this thing is invariant under conjugation and this is self-dual, this is actually the weight system in CA star, which is greater or equal than 0 because this is already a state. And this concludes the proof that if our labeling is either by alternating representation of symmetric, alternating powers of the defining representation or symmetric powers of the defining representation, then we have a state. In particular, this proves what we expected, that is all GLN, all fundamental GLN weight systems are quantum states, and in the case of GL2, well, we know that everything is an alternating power of the defining representation, so every irreducible representation is at least. So we prove that all irreducible representation of GL2 are quantum states. And it is still open whether we can generalize these to other more general representation, but it's difficult to say because dealing with these symmetrizers directly is not possible. So one has to use some trick like this to reduce the computation, but this is not always possible. I think I will stop here.
Great, thank you so much. Questions for Carlo? So for other cases, you will need maybe some other techniques, perhaps?
Yeah, you will need some other techniques. Maybe there is some combinatorial techniques known to those who study representation theory, which I don't know, might be. But it is also possible that these are the only families of states. I mean, can be. It
would be nice if one can prove uniqueness, yeah, of course, either way, right?
Yeah, but it's not always so nice.
It's not easy, of course, yeah. Great. Any other questions? Okay, if not, let's thank Carlo again for a very nice talk. Thank you.
Thank you.